Sorry, that was my starting up the live stream. It always pulls up another previous talk for some reason. We should be good to go.
Okay. Are we ready to start, Bridget? Or
yes,
yeah?
Yes, everyone is ready.
Okay, great. It's my pleasure to introduce William Boos. Bill got his PhD at MIT. That's where I first met him, when he was working on a quasi-equilibrium view of the Indian monsoon. Since then, he has done a postdoc at Harvard for a couple years. Then he was a faculty member at Yale University for a number of years, and is now based at Berkeley. Bill works on monsoons and other large-scale circulations. He has worked on, like I mentioned, a quasi-equilibrium view of monsoons. He's also thought about like topography effects on monsoons. And more recently, these monsoon depressions that he's going to tell us about today, which produce a lot of the rainfall associated with the Indian monsoon. So we're looking forward to that. So thank you, Bill, for being here. Yeah, my pleasure to have you.
Thanks, Larissa. I am going to share my screen now, and it's worked before. Does everyone see a title slide?
Yep, looks good.
Great. All right, thank you for having me, and thank you all also for bearing with the remote presentation format. Even before COVID, I had decided that I wanted to not travel as much, to reduce my carbon footprint, and doing a single cross-country flight, I think, produces carbon emissions on the order of my a full year of carbon expenditure for my two-person household in apartment living. So I am trying to travel only when I can combine things like multiple talks or a family visit with some other talk or something like that. The work that I'm going to do today is on a phenomenon called monsoon depressions. These are, I'm calling them high impact storms at the edge of the tropics. I'll get into a lot more detail about what they are, but I want to begin by acknowledging the fact that there is a lot of work in this talk that has been done by three postdocs, Michael Diaz, Vishnu, and Suhas. Suhas is currently a postdoc at Berkeley. I want to begin. I like to begin any talk on monsoons by emphasizing that monsoons are really part of, or a regional manifestation of the general circulation, the global circulation of the atmosphere. They're not just a phenomenon that happens over India. This is the precipitation climatology from the TRMM satellite for boreal summer and austral summer. And I've drawn boxes around what I think many people would agree upon as the 6 main monsoon regions of the planet. The North American monsoon maybe is the one that's closest to us. It's also the most peculiar and weakest. Most everyone knows of, or at least has heard of the Asian monsoon. But there are monsoons that occur in Africa on both sides of the equator, really in every continent that has part in the tropics. These rainfall distributions are very, very highly seasonal. You can see that there's a very wet region in local summer, is very dry during the winter time. And that seasonality is part of a planetary scale circulation that is often illustrated in this sense as a cross-equatorial overturning circulation in the atmosphere, with warm air rising in the summer hemisphere, where the Earth is receiving more shortwave radiation from its star, air sinking in the colder winter hemisphere, where you get less insolation. And because we are on a rotating planet, this thermally direct circulation is accompanied by rotational winds These symbols are meant to represent arrows going into the board where you see the tail, and coming out of the board here where you see the tip of the arrow. This would be your traditional trade winds, and those are reversed in monsoon regions to become your low-level monsoon westerlies. That makes for a lot of wind shear, meaning gradients in the wind. We see that there's a horizontal gradient from westward to eastward wind in the lower troposphere. There's also a vertical gradient in wind associated with the horizontal temperature gradient in the summer monsoon hemisphere. And these wind shears can be hydrodynamically unstable. That is going to be one of the main focus areas of the rest of this talk. I want to illustrate that by showing you at least something that might be associated with a hydrodynamic instability of that mean flow, or might cause you to think it's reasonable to expect that it might be an unstable state, which is that in these monsoon regions, we actually see a fair amount of vortex activity, and I mean transient vortex activity. This is a plot. The colors are the number of vortices that are observed per unit area, per unit time. And this includes tropical cyclones. It is done just in a broad tropical band, so we're not seeing the mid-latitude storm tracks. And so colors are basically track density. The black lines with dots are just tracks for a single year to give you a sense of what vortex tracks and genesis points look like in one representative year. A really interesting thing about this plot is you see all the vortex track density associated with the Atlantic hurricane distribution, the East Pacific hurricane distribution, and you realize that globally, the peak density for vortices in the tropics actually lies here over South Asia, in this pretty small region here, where most of the genesis occurs right over this, and not only over the Bay of Bengal, this northern part of the Indian Ocean, but over really one corner of the northern Bay of Bengal. This is an area that is home to the phenomenon that we're going to be talking about today, which are generally called monsoon low pressure systems. The more intense versions of these are called monsoon depressions. The less intense versions are called monsoon lows. And this is what those look like. This is the observed horizontal structure of one monsoon depression. Sorry, I forget what year this was, but a fairly recent, I think maybe 2006, something like that. Satellite precipitation from TRMM is plotted in colors, and reanalyzed low-level horizontal wind is shown in vectors. And so you see this, this broad circulation here, broad cyclonic circulation over the northern Bay of Bengal. The coastline is dotted in black. And so here we have India, Bangladesh would be around here, and the Tibetan Plateau would be up in this region. This monsoon depression originated, it was first observed here as a coherent vortex and then propagated toward the northwest. And these typically dump a lot of rain over land as they transit the land surface. You can see here that it's producing about 45 centimeters a day. That's a lot of rainfall. And this is one reason why these are associated with often intense floods. In fact, we've estimated in separate work that I'm going to not show you here today that over half of the hydrological over half of the hydrological disasters, meaning affecting humans in a global disaster data set, are actually associated with monsoon lows and depressions over a fairly large part of India. I also want to mention, if anyone has any questions or brief clarification points, et cetera, please feel free to stop me. It will actually reassure me that people are actually there and are listening. So feel free to just unmute yourself and pipe in, or if you're in the room, Vijit can facilitate that. So these are vortices that are easily 1,000 kilometers, and they're 1,000 kilometers wide in their outer diameter. If we look at them in a latitude versus height section, so we're now looking sort of at a vertical cross section through a composite mean monsoon depression in the South Asian monsoon. And we're seeing the black contours are the zonal wind. So you see here's the center of the storm right here at around 20 degrees north latitude. We have westerlies coming out of the page, easterlies going into the page. This is our cyclonic flow around the vortex center. And it's notable that, yes, these are warm core storms in the upper troposphere, but in the lower troposphere, they are cold core. That is one way that they are distinct from classic tropical cyclones. They're cold core storms. And they also sometimes form over land and very frequently transit land surface without any appreciable loss of intensity. And so that does mean that they don't seem to owe their fundamental existence to ocean surface evaporation. What I want to do today is pose this main science question of what mechanism creates monsoon lows and depressions over South Asia. What is the mechanism that produces the initial genesis and subsequent amplification of these storms? We're used to thinking about say tropical cyclones growing by some particular mechanism, mid-latitude baroclinic waves growing by some kind of baroclinic instability. What are these storms? That they seem to be fitting in neither of those categories, but they have been studied for quite a long time. I've put here 3 of the dominant hypotheses for their fundamental mechanisms and some of the associated papers, mainly just to illustrate to you that the study of monsoon depressions really dynamically was originated back in the 1970s. I think the heyday of work on them was in the 70s and 80s, and then there was kind of a lull in activity for a couple decades. I think we're seeing a little bit of a resurgence of interest now. One of the earliest theories, well, really the 2 earliest theories, were that these grow from either baroclinic instability or barotropic instability. Those are 2 classic types of instability, and so it stands to reason, in particular, because in that schematic that I showed you earlier, that there are both vertical wind shears that one might associate with a baroclinically unstable basic state, as well as horizontal wind shears that one might associate with a barotropically unstable basic state. It stands to reason that both of these might be candidate mechanisms. A lot of the work that was used to examine these really was fairly idealized. They would take sort of an idealized meridional wind profile from the upper troposphere or mid-troposphere in many of these papers, and just ask, is this barotropically unstable in sort of a 2-dimensional theoretical model. Another key category is to view these as sort of moist tropical vortices, and I mean vortices in which moist convection plays a key role in intensifying the storm. There has been a lot of work looking at these just as tropical cyclones that are just maybe inhibited from intensifying to hurricane, typhoon intensity by the vertical wind shear of the monsoon. Something that argues against that is the fact that they are cold core in the lower troposphere and that they can form and transit land surface without much consequence. But there is work that has been going on in your department by Angel Adames and Yiming. I think he started this when he was a postdoc at Princeton, but to view these in sort of a more general moist tropical vortex framework, viewing these as a moisture vortex instability. I'll mention some more things about that as we go on. So I want to briefly say a few things about all of these in the time that I have. Let's start with hypothesis number 1. And I'm really kind of proceeding through, in some ways, the sequence that we approached this problem. This is what I thought was perhaps the most promising hypothesis, because it seemed to be the one that recent papers by people in India who were studying monsoon depressions, they invoked baroclinic growth as the mechanism for these storms. This image shows you a climatology of the upper tropospheric temperature, contoured and annotated in Kelvin here. 247 Kelvin is the peak over South Asia. Indeed, the South Asian monsoon is the global maximum of free tropospheric temperature during boreal summer. by far, and it has a temperature maximum that stretches roughly halfway around the globe. The colors show the low-level moist static energy, gives you a sense of the moisture distribution. And we are used to thinking about baroclinic instability in this mid-latitude context where the temperature decreases as you go toward the pole. But there is a fairly strong meridional temperature gradient in this monsoon region. Also, it's just the temperature gradient is reversed. It increases as you go toward the pole. But it has been shown that that sort of meridional temperature gradient can, under the right conditions, be baroclinically unstable. There has been some work done by previous authors to try to figure out, would the South Asian state be baroclinically unstable? But regardless of whether the basic state is unstable or not, we can sort of take what I'm going to argue is a little bit of a shortcut, which is to recognize that if a disturbance is going to grow by baroclinic instability, it has to tilt up shear, by which I mean that if you look at vorticity anomalies in a typical classic mid-latitude baroclinic instability, you'll see something like this, where this is, I've drawn here on this X versus Z cross-section through an amplifying baroclinic wave, drawn a phase line of the vorticity anomalies. These are embedded in a mean flow where there's a eastward shear with height. So the mid-latitude westerlies, jet stream is strongest at upper levels. These are tilting against the shear. In a monsoon region, the low-level wind is indeed westerly, but the upper-level wind is westward because we have reversed the meridional temperature gradient. And so for a disturbance to tilt up shear, it would need to tilt from the west toward the east as you go up in height. And so what we did is we just looked at this in observations. We said, well, if we look at monsoon depressions, monsoon lows, while they're amplifying, do we see structures that are tilted like this up shear as they amplify? And this is a composite in the first third of the life cycles of a lot of monsoon depressions when those disturbances are amplifying. And we're looking here at a longitude versus height composite of the anomalous potential vorticity. That's in colors here, deep red being the largest PV. And the arrows just draw a schematic background wind, again, low-level monsoon westerlies, upper-level easterlies. And you see that the vortices of monsoon depressions in the PV sense are pretty upright. They're not strongly tilted. And if anything, they seem to be tilting a bit down shear. So instead of tilting up shear, they're actually tilting down shear. They look actually a fair amount like tropical cyclones in this composite. They look fairly different from diabatic Rossby waves, which are a fairly commonly agreed upon type of more tropical, slightly more low latitude moist baroclinic instability. So we take this as a fairly decent evidence that baroclinic instability does not seem to be amplifying these disturbances. We're moving on quite quickly to a second hypothesis for their growth, and that is barotropic.
We had a quick question.
Yeah, please. Yeah.
Bill, on your prior slide, I understand the argument that the up shear tilt's important, but another way to think about at least how the systems might grow is just by rearrangement of the PV and the vertical. I'm thinking about the cyclic development theorem. If you have regions where vorticity advection is positive in its vertical derivative, you could still get cyclogenesis. It might not be strictly a baroclinic instability mechanism. Is that part of the way one assesses it when thinking about tilts in the direction of the shear?
I think so. I hear you. So let me just repeat the question. I mean, you're asking about, I think, sort of transient growth, maybe, where there's not a classic linear instability. I think that you can still, my understanding is that you can still think of that sort of transient growth in terms of vorticity anomalies at different vertical levels, that need to at least transiently have some kind of up shear phase relationship with each other. We did look at, we did try to formulate sort of an idealized two-layer framework in which we considered these different regimes of growth, in which you kind of have a upper level PV anomaly interacting with a low level, some kind of low level vorticity gradient, background vorticity gradient. And it seemed like whichever way you phrase it, you still need to have that up shear tilt for growth.
Okay, thank you.
This paper is not only on, it does more than just present these composites, but it's titled Perspectives on Moist Baroclinic Instability with Implications for Monsoon Depressions. And we kind of walk through these different combinations of PV interactions. And I think one of those does correspond to the Sutcliffe type version. So yeah, let me know if you look at that and that sounds wrong. I'm certainly open to discussion.
Okay, thanks.
All right, so another hypothesis is barotropic growth. Well, and maybe I could just say one more thing about that. I know that Angel does have a nice paper about why he thinks that baroclinic instability isn't operating in this monsoon basic state. And so that's sort of another piece of evidence that maybe we don't need to keep exploring baroclinic instability in great depth for these storms. Another hypothesis is barotropic growth. And that is, I think, reasonable reasonable to consider because there is very strong meridional shear of the low-level monsoon flow. The red region here indicates eastward flow, the blue indicates westward flow. Vectors are just the roughly, I think 3 kilometer altitude horizontal wind. And you can see that you have a meridional shear of about 20 meters per second or so across just maybe 10 degrees latitude, roughly. And this is a composite, actually, of the state of the atmosphere over South Asia prior to, a couple days prior to genesis of tens of monsoon depressions. So this is not a climatology. This illustrates then that when you look at the atmospheric state prior to monsoon depression formation, there is very strong meridional shear. And this dashed line right here indicates the peak genesis density region for monsoon depression. So it is really strongly in this shear zone. What we did is we proceeded a little bit differently here, or maybe a lot differently. We constructed a cloud resolving model. And when I say we, really, this is work that Michael Diaz did. He constructed a cloud resolving model in which a three-dimensional basic state could be imposed. So we're really trying to go beyond what was done in those early studies on baroclinic instability, where you kind of make some idealized parabolic state of the wind at some particular vertical level and then solve a theoretical equation on pen and paper, perhaps. We are trying to use modern reanalysis estimates of what the atmosphere looked like prior to genesis of monsoon depressions, impose that as a basic state in a model that is capable of resolving convection, and then look for at least representing convection, even if we're not, I think we typically use order 1 kilometer horizontal resolution in this model, and look and see, well, how does the disturbance, how does some initial disturbance grow or not in that basic state? These are just two example equations from the model. We have a momentum equation, we have a thermodynamic equation, and we actually imposed these source terms to maintain the observed basic state. So this is really what comes out of that model. And this is a dry version of the model. So we are just taking the observed basic state and we are calculating the least stable eigenmode. We're looking for, if you excite the model with a small disturbance, what is the pattern of that disturbance that grows most rapidly? And what that looks like is can be illustrated in this life cycle, day 0, 2, 4, 6, 8, 10, as you go through these panels. And this is the pattern and its time evolution of that least stable eigenmode of that basic state. And we see here the colors represent pressure anomaly, arrows represent the anomalous wind at about 3 kilometers altitude, and the basic state zonal wind is illustrated in the black contours. So you can see the strong meridional shear here. What you see is you see this cyclonic anomaly that intensifies as it tracks northwestward, and it has an outer diameter that is very consistent with observed monsoon depression diameter. So in terms of the propagation, speed, direction, the dynamical structure, it actually looks surprisingly realistic for something that comes out of a dry model. One very big caveat is that this is the least stable eigenmode, meaning least stable, but it actually is stable. In this model, we did do a number of things. We sort of used a zonally symmetric basic state. We did runs with and without friction. When you use a 3-dimensional basic state with surface friction, your baroclinic instability that would exist in a more idealized model actually becomes stable. And this is the least stable mode. It's just weakly stable though. And when we look at its energy budget, this is a time series of the perturbation kinetic energy generation rate shown here in all the colored lines. And the black line shows the perturbation kinetic energy itself. So this just gives you a sense of the kinetic energy of a storm and how it evolves. And what we've done here is we've actually turned on a pulse of heating in the Bay of Bengal, fairly spatially confined. You could almost call it a mesoscale patch of heating. That has been switched on for the first 2 days of the simulation. That creates a vortex, no surprise. But then what we see is that friction tries to dissipate that vortex, and what acts against frictional dissipation is essentially barotropic growth. The horizontal shear, this would be the V prime, U prime, du bar dy term, is feeding energy into the storm, helping it to maintain its kinetic energy against dissipative processes. So if you can somehow supply heating, then the storm can kind of maintain itself for order 4 or 5 days, something like that. Now, what happens if we allow condensation to occur? This is just taking that same cloud resolving model, impose the observed basic state, and you're seeing an animation now of the pressure anomaly in color, low-level wind in vectors, and the precipitating, the cloud and rain condensate in colors with a color scale meant to give you something that looks a little bit like a radar map. And these look remarkably realistic. You see a vortex of roughly the right intensity. Precipitation is falling actually southwest of the vortex center, which is something that has been well observed and that we expect to occur due to the quasi-geostrophic dynamics and this meridianally sheared basic state. And the structure and propagation of these looks very much like what was happening in this least stable eigenmode. Now, that doesn't really give us a final answer in terms of what is producing the growth when we add in condensation. What we are going to do then is use more idealized simulations and systematically test sensitivity to the background state to sort of flesh out that mechanism a little bit more. So what we're doing is we're taking the same numerical model, but we're imposing a zonally symmetric basic state in thermal wind balance. That basic state, one of them is illustrated here. Zonal wind is shown in color shading. Potential temperature anomaly is shown in the contours. So it's warmer in the north, colder near the equator, typical of a classic monsoon, low-level monsoon westerlies, strong vertical wind shear, strong meridional wind shear. And what we're going to do now is assess the sensitivity of depression intensification in an ensemble of these basic states. We're going to vary the upper level vertical shear, the lower level vertical shear, and the meridional shear. So we have 2 different types of vertical shear and meridional shear. And we're also going to turn on and off interactive surface evaporation. So sort of, you could think of this primarily as wind-dependent surface heat fluxes. This is an animation that shows you what that idealized model looks like. So it is idealized in terms of its boundary conditions. It is zonally periodic. We're imposing an idealized wave number 2 for this domain structure. So you're going to get 2 depressions that spin up as time goes on. You can see again this precipitation field, peak precipitation southwest of the vortex center. You do get a sense so that this is indeed a model that represents convection explicitly from sort of just the patterns of precip that you see here. This is an example of the results. So I'm showing you now here a slice through that parameter space where we're looking at variations in low-level vertical shear from 0 vertical shear in the lower troposphere to high vertical shear in the lower troposphere, and meridional shear, 0 DUDY to large DUDY. And I'm showing you snapshots here of what the vortex looks like in its most intense state for each of these background basic state control parameters. Contours show the pressure, and the colors show the rain rate. You can see there's a clear monsoon depression-like vortex here. There is very little that's happening here, or we have no shears in the basic state, even though we do initialize it with a weak vortex. This can be better visualized if we plot the peak intensity in a matrix. And by peak intensity, I'm using the minimum central pressure perturbation relative to the environment. And we're showing here that same slice through parameter space, vertical shear, meters per second per vertical kilometer in the lower troposphere, horizontal shear, meters per second per meter as you go in the meridional direction. And you see that you get the largest intensity when you have strong vertical shear as well as strong horizontal shear. A couple other points are that the depressions seem to be most sensitive to both meridional shear and low-level vertical shear. I'm not showing you the sensitivity to the upper-level vertical shear because there was relatively little sensitivity to that. Strong vortex growth does not occur without meridional shear. So if all you have is the low-level vertical shear with 0 meridional shear, you get something that barely passes the intensity of a monsoon low, which would need to have a 2 hectopascal perturbation. It would not reach monsoon depression intensity. However, meridional shear alone, if you have 0 vertical shear, it can produce intensification. You can get a monsoon depression strength vortex. So greater intensity is kind of moving this way on this plot. And now I want to emphasize, well, why would low-level vertical shear be important? We think that it's not important because of baroclinic instability, but primarily because it's associated with a low-level moisture gradient, meaning that our low-level vertical shear is in thermal wind balance with a low-level horizontal temperature gradient. And because this is a model that we actually have to use realistic moist thermodynamics in, we can't easily decouple the moisture gradient from the temperature gradient. For instance, if you try to have a strong moisture gradient and a weak temperature gradient, you quickly run into super saturation conditions, etc. But what we've done here, and this is in one of Michael Diaz's papers, is that we've looked at time series of the central pressure of these idealized monsoon depressions. And the control model is shown here in the thick blue curve. It reaches its peak intensity after about 3 days or so. If we turn off all condensation, the intensification is not nearly as strong. There is, though, some transient growth. And if we allow condensation, but we flatten the meridional moisture gradient while preserving the temperature gradient, so this is sort of a limited case in which we could do that, you can see that the intensification does decrease a fair amount. So in these colored curves right here, these are different vertical shears, different meridional temperature gradients, but the moisture gradient itself has mostly been flattened over the the meridional width of the storm. And that does have the result of suppressing amplification by about 50%. So this indicates that the low-level vertical shear was important primarily because it was correlated in our setup with these meridional moisture gradients. Now, I want to show you that final thing that we assessed sensitivity to, which is the sensitivity to surface evaporation. We did this because if you look at motivation, in other words, if you look at a composite over the northern Indian Ocean, this again is the Bay of Bengal right here. Here's again this dotted Indian coastline. This is peninsular India right here. And what is colored here is the anomalous surface latent heat flux, and contoured is the anomalous surface sensible heat flux. Not as important. The main thing I want you to be concerned about here is the fact that, oh, sorry, I think I dropped my units, but this is a surface latent heat flux in watts per meter squared, an anomaly of easily 100 watts per meter squared in monsoon depressions. So that is an enormous surface evaporative anomaly, even though I said that these can sometimes undergo genesis over land and transit the land surface without appreciable loss of intensity. They do seem to nevertheless have a lot of anomalous surface evaporation. When that is to the tune of 100 watts per meter squared, it seems reasonable to investigate whether that could be important. And this is that same sort of matrix of intensification that I showed you before, that's sliced through parameter space, low-level vertical shear. Think of this as primarily being important because of the meridional moisture gradient it is associated with, and the meridional shear primarily being important through its association with barotropic growth. And what you're seeing here is this is the difference between when we allow the surface fluxes to be interactive and when we prevent them from interacting with the vortex. So you can see that when you have the interactive surface evaporation, it can cause the most intensive vortices, which were in this part of the plot, to become substantially more intense. Given that on the previous plot, the peak intensity was 6 to 8 hectopascals, and on this plot, we see about 6 to 7 hectopascals. It does produce a roughly doubling of their intensity. Now, this is in a model that is essentially an aquaplanet idealized model, so it may be less important in the domain where, in the part of the domain when the monsoon depressions lie over land, but maybe wishy surface evaporation feedbacks are very important for intensification as it occurs over the Bay of Bengal. So that was a little bit of maybe a whirlwind tour through some of the possible mechanisms for monsoon depressions, but I didn't want to spend all of my time with you just talking about.
We have a quick question.
Please, yeah.
Hi, Bill. This is Dan Viamon.
Hi.
This has been fascinating. I guess what's the is there a phasing between like where that moisture ends up being condensed, or where that produces latent heat in the atmosphere, the actual structure of the dynamical vortex itself that leads to that intensification? Or why is it that I mean, if you're getting that growth, there's got to be some sort of maybe in that growth curve or something. Does that make sense?
Indeed, yeah. And I'm doing something a little bit risky, but I'm trying to pull up a quick plot from a paper. Maybe, being on.
I can ask you afterward. I don't want to derail your talk, but
No. But let me. I think I can show you this quite quickly. I feel like this is an interesting plot. So down here you see moisture anomalies in these idealized depressions, and this is for without interactive surface evaporation, and this is with interactive surface evaporation. So, and the colors show humidity, and the contours show vertical motion. So you can see here that with just moisture advection, with just that background meridional moisture gradient, you're getting these sort of plumes of moisture being advected into the ascending motion in that's sort of in QG, satisfies the QG omega equation in this vertically sheared basic state. When you turn on the wind-dependent surface fluxes, you get this sort of more patchy point-wise structure. And you can see the difference, right? All this different blue-green color here is because of the ocean surface evaporation anomaly. And that is in a location that is also somewhat coincident with the ascent zone of that monsoon depression. So I think both of those are, not sure if this answers your question, but I think both of those are sort of supplying energy or supplying anomalous moisture to the part of the storm that is ascending.
Yeah.
Does that help?
Yeah, that makes a lot of sense. Thanks.
Okay. Thank you for letting me know that someone's still there. All right, so I didn't want to spend all my time talking about just theoretical dynamics. I wanted to show you some of the work that we've been doing. We've kind of been proceeding on two themes. One is trying to do basic dynamics. Other is to do something a little more practical. Let's look at past and future changes in monsoon depression properties. Around the time that we started working on these, there was a really compelling story that was coming out of some data from India's meteorological department. They have kept records of monsoon depressions for over a century. And when you just look at their record at face value, this was not something that my group discovered at all. There were papers that came out in the early 2000s from Indian authors that showed that when you look at the number of monsoon depressions going back to the early 1900s, actually the late 1800s, believe it or not, you can look at the annual value of monsoon depressions. You get around 6-8 per year, or a smoothed, I think this is an 11-year running mean in red. And you see this really steep decline from the mid 20th century through the 1980s to the early 2000s. In the early 2000s, there were these 3 years, 2002, I think, and 2010 and 12, that were the first years in over a century of record keeping when there were no depressions in this record. And we started to work on this in the year 2013 or so, and really the concern was, is the sky really falling? Are these storms just vanishing? Have we gone from having 8 per year to 0? And so what we did is we hadn't really set out to look at that story, but we had in order to do a lot of the dynamical composites, we had devised a tracking scheme. We were tracking vorticity in an atmospheric reanalysis. And we had this atmospheric reanalysis record, and we just thought, hey, it's let's just look at that reanalysis record and see, do we see that similar steep trend? Well, we looked at one reanalysis, we couldn't find a trend. So then we looked at several others. We looked at ERA interim, ERA 5, CFSR, MERA 2, the JRA 55 data set, and we compared that to the Indian Meteorological Department record in gray, and another record from India where a handful of people sat down and did sort of a hand reanalysis of surface pressure maps, just subjectively identifying these storms in sort of classic subjectively analyzed surface pressure maps. And in all of the reanalyses, we couldn't find any trends since 1979, even though in that one hand analyzed data set, this SICA data set from India, they got a fairly steep decline in the number of depressions and a compensating increase in the number of lows. We did expand the time period back to 1958, since in their record, in the IMD record, most of the decline was sort of from the 1960s, 70s onward. So you kind of need to go back before 79 to maybe be truly fair. In those two India records, these are the hand-analyzed data sets. There was a steep decline in the number of depressions, a compensating increase in the number of lows. The JRA 55 data set, we analyzed that back to the 1950s. There was no detectable trend unless we expanded the summer season to go from, instead of just June, July, August, September, to go from May through October. And then we got a weaker trend, about maybe 1/4, 1/5 as strong as in that India Meteorological Department data set. So that was a little bit unsatisfying, because we're saying, well, this one reanalysis data set might have a trend. Do we trust trends in reanalysis data sets at all? What we did is we basically said, well, let's go back to our tracking method. Instead of just tracking vorticity anomalies, let's more carefully devise a vortex tracking scheme. Let's try to optimize it for monsoon low pressure systems. Let's tune it against some of these hand analyzed data sets. Let's consider a lot of different potential tracking variables like sea level pressure, vorticity, geopotential, horizontal stream function. We saw pretty quickly that vorticity, which is what we had been using and which is what's commonly used in vortex tracking exercises, ended up looking like a fairly poor tracking variable, because it was often pretty noisy. It would produce these tracks that are kind of broken up. It was kind of hard, very, very resolution dependent. We ran an ensemble of these tracking methodologies. We had sort of broke up a lot of different reanalyses into training and testing data sets in different time periods, used a skill score, one called the Critical Success Index. This is two different sort of versions of that skill score, one in colors, one shown here on the vertical axis. And what I'm showing here is one tracking algorithm applied to the whole testing data set for each dot. And you can see that the vorticity variable, when you're tracking vorticity, it by far came out as the worst performance compared to those subjectively analyzed, sort of expert devised track data sets, and as well as agreement amongst different reanalysis products. And the best variable was the horizontal stream function, or the stream function of the horizontal wind. That was something that I think is appealing, because it's smooth, unlike vorticity, but it also, unlike sea level pressure or geopotential, it doesn't require that we assume geostrophic balance. Rossby numbers of these storms can routinely be 1 or 2. So it's nice to know that especially if you're getting in the tropics, you don't have to rely on sea level pressure or geopotential. You can just use the stream function of the wind, and that actually will perform best compared to these reference data sets. What we found is we then used that tracking data set to look at a bunch of different reanalyses. I'm going to show you, though, here one interesting thing that we found that might explain why there are trends, or why there were these steep trends in the India data set, and potentially even in the JRA 55 reanalysis, which is we took, this is not our algorithm result, this is just one of those traditional track data sets. And we ran a binary change point detection algorithm to find a year in which, we asked, is there a shift in the mean rather than a trend? Because if you go back to this curve here, it looked like there was a pretty precipitous drop in the early 1980s. Maybe this isn't just a trend, but it's some kind of dramatic shift that happened in the very early 1980s. And indeed, we could identify a binary change point, a shift, and that occurred just via that objective algorithm on this year where there's a dashed line. And the star was the year when geostationary satellite data was starting to be incorporated by India's meteorological department into their routine weather metadata maps. And this is another India data set, change point detected in that same year, and that same year still holds. When we looked at the JRA data set, it also had a change point, much weaker change, but it was a couple years earlier, and incidentally or not, geostationary data, satellite data started to be incorporated into the JRA data set, JRA reanalysis in basically in that same year that we detected the change point. So this, I think, is some evidence that, well, maybe we shouldn't be maybe we should be skeptical about whether there are trends in these long-term data sets when there are large changes in the observing network, and in this data set in particular, different methods used or different criteria used to define what a monsoon depression even is as we proceed from the late 1800s to the modern era. So I'm going to close just by briefly asking the question of, can models help? We examined trends in an ensemble of high-resolution models. This is the high-res MIP ensemble. These models did actually a remarkably good job at representing the structure of monsoon low-pressure systems. Even the weak lows had a coherent sea level pressure anomaly and a clear vortex circulation. Classic coarser resolution CMIP models have a pretty hard time getting these lows. And the models, this is a little bit of a complicated plot, but what I'm showing you here is just average numbers of low pressure systems in general in these circles, and then the breakdown into lows, which are the squares, and monsoon depressions, which are the diamonds. For one reanalysis and for each of the 8 different models that were in that high-res MIP ensemble for different multi-decadal periods. And what you see is that there is indeed, you can see the decline in the JRA 55 number of monsoon depressions, fairly modest. You see similar fluctuations in some models, but in some models, the number of depressions is going up, and others are going down. There seems to be a lot of interdecadal variability without any clear change in the number of low pressure systems, or even a sustained change in the number of depressions. Very, very model dependent, the behavior that you get, even resolution dependent in terms of here's the MRI model, the high resolution and the super high resolution model. So I'm just going to skip those last 2 in order to save maybe 7 minutes or so for questions and jump right to my summary, which is that monsoon depressions, we believe, we feel we have a fair amount of evidence that they seem to grow barotropically from low-level meridional shear with some help from convective coupling and a poleward moisture gradient. And I think work by Angel's group on moisture vortex instability is very sort of kind of fills in this part of that mechanism very well. We don't think that there is baroclinic instability, but we do think that wind evaporation feedback can enhance amplitude. Despite claims of a large decrease in depression frequency, we find that any trend in their numbers is small and might be an artifact of the introduction of satellite data around the year 1980. Projections by global climate models show no detectable change in storm counts in the next 50 to 100 years, but perhaps it won't surprise you. I felt like it was easy to skip over that slide, a fairly substantial increase in rain rates. And I'm just going to close by saying that we are using our optimized tracking algorithm to operationally identify monsoon depressions in numerical weather forecasts by India. And this is an algorithm that's running in real time with their real-time NWP output to identify monsoon depressions as in forecasts, and hopefully give some more objectively identified forecast tracks. So I'll end there, and happy to take questions.
Any questions in the room?
Hi, Bill, Dan Beaumont.
Hi.
I really enjoyed the talk. That was really just fascinating and a great outline of the different things you've done to take a look at these. Looking at the other regions where these depressions or these disturbances like grow, do you see the same sort of meridional shear and so that same sort of setup for the development of these exposures?
By other regions, do you mean like outside of Asia, like if we go to Australia or the East Pacific, or?
Yeah, I was thinking about your original tracking of vortices also includes all the tropical cyclones and everything else.
Yep.
Are that barotropic mechanism? Is that going to be the case in some of these other hotspots as well?
We have not, we have not thoroughly explored that. There certainly are the other region where you hear of monsoon depressions forming is Australia, and there has been some work done by meteorologists to really establish that they seem to have a lot of very similar dynamical structures. Monsoon depressions in Australia, monsoon depressions in South Asia. There is also meridional shear there. Another region where there's strong meridional shear is in the East Pacific. There's also a strong moisture gradient. There has been work done, I think, I know Eric Maloney has some nice papers on the potential importance of barotropic growth relevant to sort of easterly waves in that area. I think that would probably be the most, the most relevant analog in that region, perhaps. So it seems that there's a lot, and in Africa, obviously you're getting into the African easterly wave phenomenon. So I think there's been a lot of other work in different regions. We did devise a genesis index for monsoon depressions that has turns out to have a lot of commonality with tropical cyclone genesis indices. But one of the important variables is the low-level absolute vorticity, which is related to that, that shear. So I unfortunately don't have like a global, very clean answer for you. But I think there has been a fair amount of other work looking at the potential importance of meridional shear in those regions. Larissa, you have your hand up, unless there's, I'm going to be, Gidget,
I do have my hand. Yeah, thank you. That was very interesting. Lots of different stuff there. So just wanted to, you kind of glossed over this. You presented 3 different mechanisms for the monsoon depressions, but then you kind of said that 2 and 3, you're saying overlap, it sounds like. That was what you said at the end?
Yes, basically, yeah. I think that might be best summarized by perhaps this plot right here, which is that in the absence of horizontal shear, in the absence of the barotropic instability, you can get some growth, but it's pretty weak. That's in this idealized framework. In the absence of a moisture gradient or a temperature gradient, you can actually get you can get a monsoon depression like Vortex to spin up, even without a moisture gradient or temperature gradient. So we kind of, my conclusion from that is that in this monsoon basic state, barotropic growth is a necessary condition. You need some kind of coupling with moist convection because a 3-dimensional basic state doesn't seem to be barotropically unstable. I would say the details of that coupling with moist convection are still a little bit hazy to me. But what Angela's been talking about in terms of moisture gradients, that may be important. By just having a pulse of convection, you can seem to have a vortex that'll maintain itself against friction for 5 days or so.
Okay, thank you. Yeah, it's
But
too
these
bad
things all certainly seem to be additive.
Angel isn't here to see this.
Yeah. But these things certainly seem to be additive. You can find that like certain evaporation is important, moist convection is important, right? But it does seem like when you turn off the horizontal shear that nothing will really grow much.
Okay, thank you.
We have another question in the room.
Bill, John Martin here. Can you comment on any resonance that might occur between some of the natural tendencies of these vortices and the shape, the geometry of the Bay of Bengal?
Unfortunately, I can't, other than to say that we've thought about that as a very interesting idea, but haven't done much with that. I think that when you look at the basic state, there is this monsoon trough, right? It's not just a zonally symmetric shear zone. There's some zonal asymmetries to it. I think it would be reasonable to believe that sort of the edge of this trough might be more conducive to have kind of vortex roll up occurring. It may also be the case that there's friction gradients between the land and the ocean that might be important for, producing torques and generating vorticity. Having the surface evaporation maximum, though, over this Bay of Bengal region might also be important. So yeah, I don't have a great answer for you. One thing I can say is that the basic state, if you did create a zonally symmetric basic state, and you took the wind profile from each latitude in this, each longitude band in this domain, you would find that this region right here ends up being the most barotropically unstable. But when you then go from that idealized zonally symmetric framework to a three-dimensional basic state, it's no longer unstable if you include friction. I don't know if that helps at all, but it's a little bit of, we don't have a great answer in terms of, what this this particular geometry does.
Sorry to jump in. The lack of a stable eigenmode, though, I guess is less concerning given that you can still get transient growth of these things over in a system like this. So it'd be interesting to kind of choose an appropriate norm and just look at the growth, the transient growth that you get in your model rather than just the stable eigen.
Yeah, I only heard part of that.
Okay, sorry.
No. I think I mean, you're saying that the observed growth may not be an instability. It may just be transient growth, right?
Yeah, I'm just the instability of the eigenmode may be less important than just. You see this a lot in a lot of these systems where the eigenmodes are all damp, but you still get plenty of growth just because the systems are far from normal. So you get interactions with the eigen vectors for your initials.
Yeah, thanks. And both of those comments, like the geometry of these boundary conditions and that transient growth, that was kind of what we were shooting for, at least that rough idea when we were kind of doing these experiments, right? If you have some kind of pulse of heating or some disturbance. But we haven't looked at this systematically in any kind of, transient growth framework. If you have any ideas on that, I'd love to correspond separately because we haven't pushed that forward as much. And I think connecting that with observations would be super interesting.
Yeah, it's really this is what I was thinking when I was thinking that you do see that growth, that kind of propagation, or that this is different than that other than the eigenvalue here. It's nice way.
Yeah, I agree. I'll try to get in touch separately and see if you have any advice on ways to proceed.
Probably no useful advice.
Any other questions, or have we reached time? I'm happy to stay longer, but I also want to respect your endpoint.
No, I think we can stop here. We can give another round of applause. Bill, for a great talk.
Great. Thank you all. Thank you for coming virtually and in person. Hope to see you all in person sometime.
Same here.
Great. That was a really enjoyable talk. I enjoyed that a lot.
Thank you. Appreciate it. Yeah, and seriously, if you do have any recommendations on transient growth, how to better analyze observationally or consider transient growth, I'd love to hear it.
Yeah, I guess the stuff I've done with that is more like developing these sort of simple linear models and looking at growth processes with them. I don't know if your model is it doesn't seem like as much a simple linear model, the dry one. But you were calculating the eigenvectors from that. How are you doing that?
In a fairly fairly, what would you call it, like hammer, heavy-handed type way of just putting in anomalies, letting them grow, renormalizing them after a certain number of time steps.
So maybe, yeah, maybe that's sort of similar then. I can imagine like developing some sort of like estimator, like a propagator matrix or something, and then like using some norm or something to once again, my comment, yeah, I got plenty of advice. I'm not sure any of it's useful. So like putting some sort of a final structure and seeing, what actually grows into that structure, like using like a linear inverse modeling type approach or generalized or whatever those kinds of techniques do. I'm not sure that it would be I'm not sure that's a good idea. But it sounds like what you're doing is you're already showing that like, especially if you're just putting random structures in and watching how they're growing, it sounds like you're already looking at those interactions between eigenvectors anyways. It sounds like you're already done. I just wouldn't worry as much about if you're getting growth, you're getting growth, whether the eigenvector is stable or not. It's kind of like the same with the ED model that you can make the ED model stable, but you can still get growth.
Well, although I guess to be fair, we weren't really, in the dry model, we weren't getting growth. We were just getting maintenance.
Yeah. And that's what I was wondering about, whether in the non-normal sense, you can have an initial state where you've got your dominant eigenvector is your sort of growing eigenvector, but especially if there's a lot of non-normality, all these other eigenvectors kind of hide that. And in a prediction framework, then you can have sort of subtle initial conditions that experience a lot of growth. But in a sort of a maintenance of variance standpoint, then what you have is kind of like these structures that can have more variance to them, just because occasionally those other eigenvectors are covering up the eigenvector you care about at that initial state. So that's where that framework, I think, it can be kind of useful. The idea of these transient growing structures, because every once in a while, and I'm not sure that it's useful in your case, but every once in a while you get these structures that the initial state, because of the way the different eigenvectors kind of cover up your initial, the eigenvector you care about, they cover them up in ways that don't necessarily look like, say, the adjoint of that eigenvector. So your initial state may have maybe pinging different structures in different areas that can then grow just because all the other eigenvectors die off. But again, I'm not sure that's.
Well, no, but that's interesting, because I think that does point at, though, something we haven't done, right? Like we sort of used some kind of pulse of heating to excite, a mode.
Yeah.
But we didn't sort of consider how different modes would superimpose in a time transient fashion.
Yeah, I just think, you can get a lot. I mean, and I'm not sure I'm not convinced that it's a useful thing for what I'm suggesting here. I think what you've done is a really good job of showing, especially once you add in the moisture, you get all that additional growth of whatever structure you have there. So I think that's probably the most interesting result. I doubt you're going to get different from that. So I don't know.
Yeah. Okay. Thanks. Well, it certainly gives me some things to think about. Yeah.
Yeah, I'm not sure if it's I'm not sure. Anyway, it was a really enjoyable talk. I really enjoy your breakdown of the analyzing the baroclinic, barotropic, and then adding the moisture in. I thought really a nice way of looking.
Great, thanks. Yeah, I hope it wasn't too scattered, but
Not at all.
you
I thought
kind
it
of
was
sort of want to
amazing.
summarize a lot of.
Yeah, I thought it was amazingly clear, like a really nice story that you told. I thought it was